Hello, good day, Jules there. We are here today to talk about the energy price prediction in Colombian energy market using machine learning models, which is the result of the hard work of Team 88. Before we start, I would like to quickly introduce ourselves. Team 88 consists of 5 members: Jairo Ruiz, David Zambrano, Sebastián Castro, Carlos de Oro, and Pedro Diaz. We made this project for Conexa Lab, a company based on Bucaramanga, focused on the management and environmental development of sustainable smart territories. Currently, due to the low certainty of future energy prices, their financial studies are not as robust as they would like. As a result, energy projects cannot become attractive to their customers. So, Conexa Lab is in the need to integrate into their studies a forecasting price of the energy for the coming years. By the forecasting of energy prices in Colombia, we contribute to the reduction of the uncertainty around future prices, and especially, we will provide Conexa Lab a new and powerful tool to improve their calculations on the expected returns on clean energy investments, which in the end seeks to contribute to optimizing the use of resources in order to foster his clients to be more friendly with the environment. Now I would like to explain how the energy price is established in Colombia. The unit cost is the result of adding up the costs incurred by companies in carrying out a series of processes: generation, transmission and distribution, commercialization, and other regulatory components. Generation is one of the components that have the greatest weight in the unit cost, around 35%. Given the complexity of the other components, it's prudent to analyze only the generation component for now. This component is defined based on the energy stock price, which is easily explained as follows. The price and energy supply are assigned by auction every hour, where generators offer the amount of energy that they are available to produce at this hour and the corresponding price to be sold. This price is fixed once supply reaches demand for energy at the given hour, and the energy sold is the one offered by generators whose price was equal or below the energy stock price. Our principal source of information is XM, which is the sole operator of the electric power grid in Colombia and has the main electric market datasets available for public access. The dataset extracted from XM includes historical data of the supply and its availability, pricing, and hydrological data. Due to the electricity sector in Colombia is dominated by large hydropower generation, around 65%, which has the more influence on the market.
The data analysis was focused on the generation of hydroelectric energy. Since most thermal power plants use gas as fuel, the governmentally regulated price of these hydrocarbons remains stable and the cost of generating this thermal energy doesn't vary too much. Here, we observe a price chart, which is generally well behaved in terms of stationarity. Some peaks can be seen, the largest being at the end of 2015 due to a severe drought. The box plot by years confirms the information we have seen on the last time series. In the box plot by months, we see strong influences by weather changes, where rain seasons and droughts affect energy market price. Here we can see the severe drought that occurred between 2015 and 2016, provoking a drop in the waterfall. The resulting power reduction in hydroelectric plants leads a large increase in the energy price. The following diagram shows the evolution of the main energy sources over the time. In the graph, we see the power generation per year, and increase in hydraulic energy generated over years is observed, with 2018 being the peak. Meanwhile, the thermal plants show highly variable behavior over time. On the other hand, cyclical behavior can be seen in the average monthly generation. For example, in February, the production of energy drops. This is due to the phenomenon of El Niño, which caused severe droughts. The opposite is seen in July and August, where we encounter the phenomenon of La Niña causing large amounts of rain.
That the correlation of the hydrological variables are positive, with the contribution with a highly variable correlation. In a similar way, it can be seen for the discharge and reserve variables. In the flow contribution graph, a clear trend is not noticeable, but we see that in the last years, the water reached the most in the reservoirs were 2015, 2011, 2017, and currently 2021. On the other hand, in the graph of water volume discharge, we see that between 2001 and 2007 and 2013 to 2016, less water is evacuated than the situation in the years 2011, 2018, and the current year 2021. Additionally, in the graph of daily volume in the reserve, it can be seen that since 2017 to today is an increase in the total amount of daily water stored in the reservoirs compared to previous years. Otherwise, For the water volume discharge diagram, no clear relationship to price can be observed. However, in the flow contribution graph concerning the price, we can see that in some days the flow contribution to the reservoir decreased and the price had very higher values than expected. And in the discharge graph in water volume, we note that there were days with high prices when no water was drained from the reservoir.
Our machine learning models were meant to capture all the information from the historical behavior of different variables, including hydraulic and thermal availability, flow contributions, daily volume measured in millions of cubic meters, volume, and daily useful volume measured in gigawatts per hour, to build the energy price forecast, as well as their interactions and effects over our variable of interest. As we mentioned before, we studied and analyzed in depth the time series to determine weather stationarity, trend, and seasonality in order to identify the deterministic components of every variable using the time series decomposition from traditional models and from neural networks models. They solve this problem in different ways but complementary. These are the graphic representation of the results for the variable of interest energy price. The second step in understanding time series behavior to forecast was to determine the order, direction, and strength of the autoregressive and moving average process structure. To solve that, we started with the lag plots, autocorrelation functions, and partial autocorrelation functions of every time series. What we found so far was useful, but not enough to reach the desired forecast. From our exploratory data analysis, we knew that stationarity conditions weren't fulfilled, so a data transformation was required, and following the econometrics theory, the first difference will solve most of the problem. What we found after applying the first difference to the series was impressive. Here, we compared the density functions of three variables: energy market price, hydraulic energy availability, and daily useful volume before and after the transformation, improving the behavior of all our series as the corresponding QQ plots indicates. Finally, our machine learning models are ARIMA, Sorimax, and Neural Profit. The specification of these three selected are the best performing after having tested more than 150 different models to project every series required for this exercise. Given that parameters of each model assign different values to the information that is incorporated into them, the results they deliver are also different. And for these reasons, we decided to add an additional projection, which is the average of the former forecastings. This average has the advantage of reducing what might be the most extreme values of each model with respect to the others. One of our greatest contributions to our machine learning models understanding that the greatest difficulty with time series models is trying to be consistent in long time horizons because it's very difficult to anticipate unexpected events that affect the variable of interest. This is why we estimated and incorporated the corresponding impulse response functions from the Sorimax models to simulate different types of shocks on our projections and apply them over all the forecast as an interactive option in our dashboards.
In the dashboard, we see the description of the project, and in the access button, we can find watch video, access to the code, and our CV. Joining the app, we find the description, the prediction, and the glossary. In the description tab, we show the power generated and the contribution of the flow to the Colombian reservoirs. Also, we find a small guide to the use of the models for energy price prediction. Here we can see the year you want to visualize the models. For example, 2021, and the most important thing is to see the shock to an explanatory variable to the original prediction. For example, taking the current date, choosing the model, the variable affected by the impulse, impulse magnitude, cumulative impulse, and the convergence for the forecast applied impulse. We see that the orange line is the original prediction and the green line is the prediction with its impulse.